Okay, we're recording. So this atom over here, which had an equal number of protons and an equal number of electrons, was electrically neutral, now just lost an electron because that electron went into the positive post to try and make an atom over here neutral. So what happened to this? The electron went this way. What happened to this atom? Did it become positive, negative, or stayed neutral?
Positive.
Electron left that atom and went
It's
over.
positive now.
Yeah, now it's got a net positive charge. All right, notice it's not the positive didn't move, but the atom becomes net positive because there's more protons now than electrons. Now this atom over here has got a net positive charge. Remember that like charges repel, so this negative over here is trying to repel the negative electrons. Unlike charges attract, so this is trying to attract electrons. So now an electron from here goes over into this atom. So now this atom over here now picks up an electron. So this atom does what? Positive, negative, or neutral?
Neutral.
It goes back to being neutral because the electron that it lost is now replaced by this electron. But now this atom over here becomes what?
Negative.
It lost an electron.
Positive.
So it becomes positive. So this net positive moved over to there. Because this one became neutral. This, because it gained an electron. This one lost an electron to go over here, meaning it's got more protons than electrons, which means that it's net positive. Then that happens over here. An electron from here goes over to this atom. This atom over here gets the electron it lost, replaced by the electron that just came in. So it now becomes neutral. But this atom over here lost an electron. So it becomes net positive. And then that same process repeats over here. We got an electron from here, goes into here. This atom that electron that was lost is now replaced by this electron. This guy goes back to being neutral. This one lost an electron, so the net positive charge moves over to this atom. An electron from here moves over to here, replacing the electron that was lost. This guy goes back to being neutral, and this one now is net positive because it's lost an electron. So the net positive goes that way. So the net positive, the electrons, moved this way from negative to positive. The net positive moved from positive to negative. So the difference here is conventional, let's talk about electron flow. Electron flow, the electrons move from negative to positive. In conventional current flow, the net positive charge or the net positive charge moves from positive to negative. All right. So the key thing here is, and it's important to realize that we're going to use the conventional current flow. So for us, current which is the movement of charge, and that's one thing we're going to talk about in a second. Current for conventional current flow is always going to be from positive to negative. Even though it's the electrons that move, we're going to remember that current, which is the movement of charges, is going to be from positive to negative. That's what we call conventional current flow. All right. So that takes us to some definitions. Current is the movement of charge through the circuit. And in our case, we're talking about the net positive charge. Okay, so current is what we're going to look at. The designator for current, if we're going to put current in a formula, the designator we use is I. The I stands, well, it was originally in French, but for us it's intensity. It's the intensity of the charge flow. How much charge flow do we have? How many charges flow through the circuit? And we mentioned last time charges are in coulombs. So how many coulombs through the circuit? The intensity of the charge flow is what we use. And the units of current that we measure current in is the ampere. Named after the physicist Ampere. Okay? And we abbreviate the ampere just as a capital A. Okay? When we think about batteries, and we're going to get a little bit more into the physics. I want to go through some stuff fairly quickly today. We're going to go through the physics a little bit more when we get into chapter 2 or 3, I guess. But I want to get through a little bit of stuff today, really to help you in the lab this afternoon. You can think about voltage as the force trying to move charge through the circuit. Right? It's the voltage, and the voltage would be rated in the battery. We think about a car battery is usually 12 volts. If we think about a little flashlight cell, usually these guys are about 1.5 volts. All right. So we call that the force trying to move the charge through the circuit. The designator for the voltage is V. So if we're going to put it in a formula, voltage in a formula, we use the letter V. The name comes from Andre Volta, who was an Italian physicist. And the unit that we measure voltage in is the volt, which we abbreviate with a capital V. Okay?
Are both of them capital V's?
Yes, both of them are capital V's. Good question. Thank you. The last part of the picture in a circuit is the resistance. And the resistance is the opposition to charge flow. since we said that the flow of charges is current, we could also say that the resistance is the opposition to current. Okay. The designator what we would use in an equation is the letter R. And the unit is the ohm, which was named for Georg Siemens Ohm, who was a German physicist. We don't write out the word ohm and we don't use an O. We usually use the Greek letter omega for ohms.
Is it gonna matter like the nationalities? Like, are you ever gonna ask us that?
No, just it's just nice to know that a lot of these units were named after famous inventors. So you had ampere, volta, and ohm all had electrical units named after them. Okay, we good up to here? Okay, let me. There's a relationship. So let's think about this for a minute. So if I think about my circuit over here, I have the battery trying to make the current go through the circuit. I have a light bulb, and the light bulb is going to have some resistance to it, some number of ohms of resistance that's trying to keep that current from flowing through the circuit. And we have the amount of current that's flowing. All right. So if I go over here, one of the things that Ohm was famous for is what we call Ohm's law. And Ohm's law says that the amount of current flow is directly proportional I have to move this a minute. To the voltage and inversely proportional to the resistance. So what does that mean if we take away all the math speak? I forgot to tell you, if you have a camera, I ask that you turn it on just so I can see who's here and who's writing and who needs extra time to maybe do some writing. So if you've got a camera, turn it on. Okay, so what does that mean if we think about the math speak? Current flow is directly proportional to the voltage and inversely proportional to the resistance. Directly proportional means what in math speak? If we translate math speak into real English, what does that mean? It's directly proportional to the voltage. So that means if I make the voltage go up, what should that do to my current if it's directly proportional?
Go up.
It will also
Go up.
Okay, means that if the voltage increases, the current increases. And what about inversely proportional to the resistance? If I make the resistance go up, what does that do to the current?
Goes down.
It'll go down.
It'll go down. So if the resistance increases, the current goes down. So that means that if I wanted to set this up as an equation, what would that mean in terms of where does we know that the current, okay, is going to be somehow related to the voltage and the resistance. So the voltage and the resistance are going to end up on this side. So what does that mean? What, both on the top, both on the bottom, one on the top, one on the bottom, what?
V over R.
V over R. So either you knew that or you figured it out. Let's think about it. If I have a fraction and I make the numerator of a fraction go up, make the numerator of the fraction bigger, what does that do to the value of the fraction? Right? If I think about this, if I have 1 over 4 and I change that to 2 over 4, what just happened to the value of the fraction?
It got bigger.
It got bigger, means that the top means it's directly proportional. If we think about the other end, if I have a fraction 1 over 4 and I change the denominator, I get rid of the 4 and I make this 1 over 8, what just happened to the size or the value of the fraction?
Smaller.
Went down. So the resistance goes up and the value goes down. So it's inversely proportional. So this is Ohm's law. And of course, we can also change that around. If I cross multiply, I can get that V is equal to I times R, or I could get that R is equal to V over I with a little bit of cross multiplication. Okay. So if I look at our example, if the battery in that previous example was 12 volts and the bulb resistance was 6 ohms, Ohm's law says the current that should flow is V over R. So I have 12 volts over 6 ohms, 2 amperes. Everybody with me?
Yep.
Just as a point of information, whenever you work on problems, either on homework, on quizzes, or exams, always show me the formula, the substitution into the formula, and the result. For a bunch of reasons. If you're doing a homework problem and you're going to do homework and you're going to study on an exam, okay, if you write it out this way, that's going to be a lot better than I sometimes get on some exam papers, which are like, okay, and I every year I threaten to do it, and someday I will. But always show me formula substitution result. If you looked at this stuff over here and tried to figure out what you did when you're studying for the exam, you're not going to be as successful as if you did it in this format. You'll be able to look at it and go, oh, this is the formula that I used. These were the numbers, let's see, the 12 volts came from here, the 6 volt ohms came from here, and this is when I did the math, I got this. Okay, so you'll be able to backtrack and figure out exactly what you did when you go to study. On a quiz or on an exam, if I saw this, I would look at that and go, well, the person used the right formula. They plugged the numbers in right, but obviously they screwed up when they used the calculator. So this one shows me you know what you were doing, you just made a mistake on the calculator. This one over here, if you had this on your exam, I'd be going, beats me what they did. Okay, so for your own benefit, for my benefit, mostly for your benefit, always formula, substitution, and result. Okay. All right. So just as a heads up, I had a dentist appointment that I had scheduled for months and could not move. So I have to leave at the latest quarter of. So I'm throwing stuff at you quick. I'm sure that Professor Atwood's going to go over a lot of this with you. If I don't get to the component recognition, I sent him a copy of it this morning. So if I don't finish it, he can go over it with you. All right. Okay. So let's do another example to lead into something else I wanted to talk about. Let's say I had this. If I did that, then when I said I equals V over R, 12 volts divided by 2,000 ohms.
Hey. Hey.
0.006 amps.
What's up? You came too fast.
All right. What about if I had V was 10 volts and R was 1,000,000 ohms. Now we've got I is equal to V over R. So we got 10 volts divided by 1,000,000 ohms. Point 0.00010 amperes. I think that's right. Pretty soon we figure out that all of these zeros, both here and here, get to be a pain in the neck. And they figured that out a long time ago, and they came up with, and you've taken a science course before, you heard about scientific notation. And scientific notation is just a way of getting rid of extra zeros and leading zeros, so we don't have to write them. If I wrote down this number, what is that?
1,000?
1,000, right? 1,000. So in scientific notation, we come up with what are called prefixes. All right. And we're going to get into the prefixes in a lot more depth and get into the math of it a little bit when we get to chapter 1, actually. But again, you're going to see stuff this afternoon, which is not going to work out. I could write this as 1 times 1,000, yes? Is that valid?
Yes.
Yeah.
Okay. There's a metric prefix that we can replace the times 1,000 with the letter K. So we could say that this is equal to 1K. 1K means 1 times 10 to the times 1,000. Well, 1 times 1,000 is 1,000. So this becomes a shorthand way of writing this. What about if I had this? What would that be?
40K.
40K.
Yeah, that would be 40 times 1,000. Or since the times 1,000 is a K, 40K. They also have another prefix. Let's say I had this. What's that equal to?
1,000,000.
1,000,000, which would be the same as 1 times 1,000,000. And we use the metric prefix capital M to represent the times 1,000,000. So we could write this as 1, and this is, by the way, called 1 meg. So this would be 1 meg. So metric prefixes and scientific notation are nothing more than shorthand ways of writing really big or really small numbers. That's the big side. What about if we have the small side? What if I had this? What is that?
0.1.
Yeah, 0.1, but what is it if we don't talk about it as point something?
1/10.
1/10, right? 1 divided by 10. Okay. What about if I had this?
One over 1,000.
1 over 1,000, which would be the same as 1 times 1 over 1,000. Yeah?
Yeah.
We have a metric prefix for that. The 1 over 1,000 is lowercase m, which we call milli. So we could write this as 1 lowercase m, 1 milli. Okay? So we could do that. What about if I had
One over 1,000,000.
1 over 1,000,000, or 1 times 1 over 1,000,000. And the prefix we use for that is the Greek letter mu, which we write or speak as micro. So again, we have shorthand ways of writing very small numbers or very big numbers. Here's a tricky one. What happens if I have this? What happens if I had 2,700. Any
2.7.
ideas on how we'd write that?
2.7K.
2.7K. We'd have, in order to think about this, what do I have to multiply times 1,000 to get 2,700? And that would be 2.7. So 2.7 times 1,000 is what gives me my 2,700. So I could write this as 2.7K. So if I'm converting over, the easy way of looking at it is, if I want to go to K, I shift the decimal point 3 places to the left. If I want to go to meg, I shift the decimal point 6 places to the left. So if I looked over here, I would have 1, 2, 3, put the decimal point there. That would be K. And we'll see why this is when we look at scientific notation in more depth a little bit later in the course. But as it sits right now, if I want to go to, I'm going to write them up here, 2K, move the decimal point 3 places left. To meg, move the decimal point 6 places left. If we want to go to milli, lowercase m, we're going to move the decimal point 3 places right. And if we're going to go to micro, we're going to move the decimal point 6 places to the right. And again, I'm just throwing you the how you do it. We'll talk about why we do that next class. All right, questions? All right, I've got to head out, so I'm going to let everybody go now.
Would you give me 1 second? I gotta copy it down.
Oh, sure.
Is there a way I can view this recorded class?
Yeah, what I'm going to do is I always record it on my computer and then I edit it. So if we do a problem session and you take 10 minutes to work on problems, I edit that out so you're not watching you sit there when you already did it. So I'll edit it, put it up on my YouTube page, and then send out the link to the class for today's session. So I'll probably get that done. Like I said, I have a dentist appointment now. I have to do one other thing after that. And then I'll edit it and send it out tonight.
No problem.
On that note, what's your YouTube channel called?
It'll be in the link. All right.
Thanks.
Anybody else need more time? Okay. I'm sorry about having to cut you short. However, like I said, I scheduled this like 3 months ago, and the way dentists are now, next appointment I would get would probably be next year sometime. So we're going to cut it. All right. I'm going to end the program and then see you all on Tuesday. All right. First, I need to stop the recording.